I'm Jake Oshins. I'm a hardware and software architect at Microsoft. Over the course of my career, I've worked on operating systems, hypervisors, and particularly device virtualization. And these days, I'm working on the hardware that underpins Microsoft's cloud, Azure. Today, I'm going to be talking about NVMe as an interface to cloud services. This differs from NVMe as an interface to local flash or even a spinning disk, but it's still storage. And I want to talk about why we might even consider it for things broader than local storage or even small scale storage into the cloud as a whole. We need to make a choice when we are providing an interface to our customers. Traditionally, that interface has been through paravirtualization. We see device drivers that are meant for virtual machines inside those virtual machines, providing abstractions like a SCSI controller. And while that does work very well, it doesn't work at the line rates that we're starting to see. We're at 200 gigabits today. We don't see any point at which those speeds stop growing. And if you try to do paravirtualization at that speed, you end up paying a very large cost in terms of overhead, and it makes it impossible to reach these bit rates without considering hardware interfaces. So we want to give an interface to cloud customers that allow them to get at their storage. And we could do things like invent a new SCSI controller in hardware, or we could make a completely custom cloud storage interface, or we can pick an interface that exists. And there are a couple of interfaces that exist in the NVMe space. One is NVMe over Fabrics, which is, of course, meant for attaching to lots and lots of remote storage. Even then, though, the interface choice is not entirely solid, right? It's different for every NIC, and there's an NVMe driver in every operating system. The boot path through NVMe works quite well. And in fact, if we use the PCI attached NVMe controller, which is very well known, the customer doesn't have to deal with all the network configuration issues of NVMe over Fabrics, along with those NIC drivers, secrets and such. Also, if you expose a PCI device directly to the customer, you can integrate things like compression and encryption in a way that are more difficult to integrate with NVMe over Fabric. However, NVMe for remote storage is not quite a perfect match. It's actually a little bit of a semantic mismatch. An NVMe controller comes with the assumption that all of the media for all of the NVMe namespaces are uniform in latency and other characteristics like caching. Most existing software pairs queues with processors, not namespaces. Each queue becomes a separate initiator with symmetric view and usage of the backend storage. This works all right, but if what you're looking at is a very large amount of backend storage, mixing a whole bunch of different storage on a single NVMe controller ends up violating the expectations that the software stacks that use NVMe have already got baked into them. As an example, Linux will stop issuing tags for I/O, suspending an application's threads if you have a slow NVMe namespace on the same controller as a high throughput namespace, even if the application is only using the high throughput namespace, if I/O starts backing up to the slower namespace. This is basically a head-of-line blocking problem. The scope of today's NVMe controllers are really meant for a subset of a whole host. The Open Compute Project's Cloud SSD, for an example, is a device that has usually around 64 functions. It could scale up to 255, and the expectation is really that there's several of these, or if not many of these, inside of a single host. Each one has 2 to 4 PCIe lanes and a certain amount of media behind it. And so the amount of storage that each function exposes is a fraction of that media, and it's a relatively small scale for each of them. We wouldn't ask a device like this to have lots and lots and lots of interfaces, because splitting a single piece of flash media into thousands and thousands of pieces doesn't really make a ton of sense. But you know, and an SR-IOV device would have the same properties, right? Maybe it scales a little bit more. It might have a few more PCI lanes. It might have a few more virtual functions, even in the low thousands. But if you're just splitting up a single SSD, there's a natural limit to that. When you have a SmartNIC, though, connected to, say, today's cloud host, and that cloud host could have hundreds of cores and could have thousands of containers running on top of it. At that point, you're fronting for, you know, petabytes of storage rather than that which fits within a single SSD. And making a virtualizable NVMe controller that scales to petabytes and thousands of consumers necessarily involves changing the way that interface works. We couldn't simply ask today's physical function NVMe controllers or even SR-IOV controllers to hit that type of scale. Beyond the scaling problem, today's NVMe controllers are difficult to virtualize in a nested sense. Imagine an NVMe controller with 50 namespaces. Now, trying to imagine splitting those namespaces out to different virtual machines. You can certainly do that at one layer, but if you have 2 layers of virtualizations, either a hypervisor running within a hypervisor or a container host virtual machine with lots and lots of containers, and each of those containers might be using technologies like VFIO or SPDK, which again try to split that up. The definition of an NVMe controller today pretty much lends itself to a single consumer. And using this in a cloud environment often involves multiple layers of consumers, sometimes under control of different layers of the customer software with middleware, the hoster's software or hardware. And we need a controller definition that's more amenable to nesting. So NVMe over Fabric already has a solution to this. It's called Scalable Resource Management. I mean, it's working its way through the NVMe committee. And it's a mechanism for building logical controllers out of large pools of queues and namespaces. It leverages the concept of an admin controller, and from the admin controller, create extended controllers. And each extended controllers is really just a set of queue pairs associated with a set of namespaces. It's relatively cheap and lightweight to create a new extended controller. The extended controller is, again, just more queue pairs and an association with namespaces. In NVMe over Fabric, the RNIC or RDMA NIC queue pairs take the place of the NVMe queues, and the cost of a new controller is really just the cost of a new set of queues. What we'd like to do is bring that concept to PCI attached NVMe controllers. The exact same concepts apply, we believe. We can take a controller that has a whole lot of Q pairs in hardware and associate those with extended controllers using the same sort of admin controller interface that NVMe over Fabrics has today. That comes with a few things that NVMe over Fabrics doesn't require. For instance, a bus tagging mechanism on the PCIe fabric to associate each flow over PCI Express with a different set of address translations. In PCI Express, things tagged on the bus can go through two sets of translations, one associated with a virtual machine and one associated with processes within the virtual machine. If creating an extended controller is also associated with the correct bus tags, we can keep this sort of traffic separate and we can create extended controllers in the same way that NVMe over Fabrics does. So if we're going to do that, I believe that there's a set of things that have to be true, a set of tenets, in order to make this efficient and scalable. Let's look at SRIOV for devices for a moment. One of the problems in SRIOV is that you pretty much have to build an MSIX table for every virtual function that has as many MSIX table entries as the NVMe controller has Q pairs in order to operate efficiently. And so if, say, a SmartNIC has 1,000 Q pairs, you would need as many MSIX table entries on every virtual function, because they all have to be the same with SRIOV, that you would have for the largest virtual function you want to give to any one customer. So if you want to, say, give an NVMe controller with a couple hundred Q pairs to a particular customer, you have to have a couple hundred Q pairs potentially on any virtual function on every MSIX table. And this basically forces people to find solutions that allow you to have MSIX table entries that are multiplied by the number of virtual functions. Similarly, the virtual function itself has to have enough memory mapped space for as many Q doorbells as could possibly fit. We believe a solution here, in line with Scalable IOV, which is a topic happening in other forums. I'll talk about that in a couple of minutes. We think that we shouldn't have to replicate these things. We shouldn't have to replicate MSIX table entries. We shouldn't have to replicate doorbell space, because they're really only in use by one customer at a time. We don't want the hypervisor to have to interpret things like an admin queue in order to accomplish nested virtualization. We don't want a configuration space for every interface. That doesn't scale to tens of thousands. We don't need a control and status page for every controller interface, just as NVMe over Fabrics doesn't require it. We don't think that we need it for a scalable NVMe controller. And we need the virtualization of Q numbers and MSIX table indices as referred to by Q pairs and such to be done entirely in firmware without adding additional hardware. So what would the mechanics of that look like? Think about an NVMe controller. The primary controller is an admin controller. In its simplest mode, it could also be a data controller, but probably it's just an admin controller. And each of these, it creates a pool, and we can create one or more extended controllers. In order to do that, you'd send the same sorts of commands to the admin queue on the admin controller that you would send to the admin queue on an admin controller in NVMe over Fabric. And as the extended controllers are created, they suballocate from the underlying hardware resources. So we probably have a hardware limit in the number of queue pairs, but you can create as many admin controllers, or sorry, as many extended controllers as you like until you hit that sort of a limit. So up to this point, the mechanics we're talking about on the previous slide are about how that would be the same as the NVMe over Fabric's view. There are parts that are different. In order to make this map onto to a PCI controller, we have to associate a bus tag. There are a couple different types of bus tags in the PCI specification. One is the requester ID, another is the process address space ID. And in today's PCI implementations, the requester ID is the key for the second level page table translation that translates guest addresses into host addresses. And the process address space ID is a key for the first level of page table translation from a virtual address that an application, a user mode application uses to that of the kernel that runs within. And we would need to associate these with specific extended controllers so that the traffic that comes across the PCI Express fabric is in fact tagged correctly for each one of these extended controllers. So the right page tables are used so that the each logical controller, each extended controller is isolated to the customer that's using it and efficiently moving data to and from that customer's application. The host relative view of the controller needs to be flat, right? It needs to not rely on the hardware itself to do anything other than put the right tags in place and substitute the right QIDs and the right namespace IDs as things flow through, so that we're not asking the hardware to do arbitrary levels of nesting. We need to define that in such a way that the firmware takes care of all the complicated parts and the data path is quite simple. So in order to get all this to happen, we're currently talking through the mechanics of scalable IO virtualization in a working group in the Open Compute project. A bunch of companies come together to talk about this, to talk about exactly how the bus tags need to work in a scalable environment, how management's done, how confidential computing is done, and how each of these things will ultimately fit together. There is in fact a release 1 of Scalable IOV in the Open Compute project. I don't think it's quite sufficient in order to build a scalable NVMe controller. That's my main motivation for being in this working group and trying to get to a second version of this. When that's true, and when that's done, we will be taking the output of that and trying to work with the PCI specification and the CXL specification. And at that time, we'll be coming to NVMe Express to try and standardize the entire scenario once the underpinnings are taken care of. My main motivation for being here in front of you today to talk through this is that I'm looking for people who want to be involved in this, who want to help me drive the direction and to speak up for other stakeholders in this discussion. And we hope that you engage with SNIA in order to accomplish that, and they can get you to me or to other people who are involved. Thank you so much for listening to me. Please do take a moment, rate the session, and we want to hear from you. We'll be responding to all your comments and questions. Thank you very much.